Hi, I'm Gary McGraw. I'm going to talk today about security engineering for machine learning here in one of the Biml in the Barn talks. A little bit about me. I started out, as many of you know, in software security, but before that I was a machine learning person in grad school. And after retiring, I wondered what had really happened in machine learning. So I started taking a look with some friends, and we formed a group called the Berryville Institute of Machine Learning, which I've been doing now for about 3 years. And I want to talk to you a little bit about how security engineering and machine learning come together. This is part of the Biml series of talks, and we're going to have a bunch of people talking about security engineering and machine learning. I guess this is my version, and I'm going to talk about the results that we've come up with at Biml since January 2019. First, I thought it'd be good to give a very brief introduction to ML just to kind of set the stage. There's a lot of confusion in the popular press about machine learning and AI and deep learning and deep neural networks and all of these things and what is what. And so I thought I would borrow some material from Melanie Mitchell, who wrote this great book, Artificial Intelligence, a Guide to Thinking Humans, and show how machine learning and AI have changed over the years. Back in the 50s and 60s, when artificial intelligence was first introduced by McCarthy and others, it was a big field, included lots of things like search, breadth first, depth first, all those things. And machine learning was a small part of that, really mostly focused on Bayesian models. And deep learning was an even smaller part of that, perceptron networks and so on. But really in the 1990s, machine learning got much, much bigger and started taking over parts of AI, although deep learning was pretty small. And then around 2000, 2010 area, machine learning and deep learning in particular, the idea of neural networks that have many, many layers that learn with back propagation and may involve convolution networks, things like that. But many, many, many nodes came to take over in the popular press. And so we have people talking about AI when they really mean deep neural networks, or people talking about machine learning when they really mean deep neural networks, and so on. And today, I'm going to focus most of my attention and most of the risks that we've identified at Biml around deep learning models. And so the idea is neural networks which try to model the way the human brain works. And so here's an example on a slide. You've got a person looking at a picture, and there are various layers of processing that happen V1 through V4. And basically, you move from pixels up in representational space to object recognition. You go, oh, that's a dog. And what a deep neural network is trying to do is really the same thing. We have a bunch of layers. At the input layer comes raw input, and that feeds up through the network, and we get to object recognition layer, the output layer, which may say something like 85% dog, 15% cat, which is kind of a crazy way of saying it, but that's the way neural networks work. So I'm going to be mostly focusing my attention on that. Models that learn to their behavior by being shown input over and over and associating that in an automatic way with output. So that if you show a huge data set millions of times, then the output eventually trains itself up to be what you want. So machine learning systems come in a huge number of shapes and sizes. And one of the things that we wanted to do in our work is try to build a generic model so that we could think about risks and think about risks tied to particular life cycle stages in a network. And so we came up with this generic machine learning model, which has 9 basic parts, and we also think of the whole system as part number 10. But I'm going to explain those basic components and talk about how risks are associated with each of those components in this talk. In this picture that you see here, the processes are ovals, and collections of things like data sets are rectangles. And arrows represent information flow between those components. We use this model to think about risks in each component. One of the things I want to address before diving into the risks is, and even attacks, is that nomenclature really matters. There are a lot of people that are calling this field adversarial machine learning, which in my mind implies intention on the part of an attacker doing bad stuff. That is, if you're going to do an attack, you're going to have an adversary. Your adversary is going to have intention. But sometimes security risks don't really require an attacker intentionally attacking you to carry risk. Insecure systems invite attacks. And that's why at Biml we like to call this field machine learning security. And we like to talk about risks instead of attacks, something which I'll come to more in a minute. Without further ado, a lot of people have spent a fair amount of time talking about machine learning attacks, particular attacks against particular machine learning systems, and trying to generalize some knowledge from that taxonomy. So what we decided to do is really simplify the attack space into a attack taxonomy that looks like this. It has 6 particular parts, and we've got things like data manipulation, input manipulation, and model manipulation down one column, and then on the other column you can see extraction attacks, data extraction, input extraction, and model extraction. And there's some examples for each one of those. For example, if you're manipulating the input, you may be doing an adversarial example attack, about more which later. The thing is that attacks have really great sex appeal, but they don't even really begin to cover all of the risks at all. And so, you know, data manipulation might be one kind of attack, and we can talk about a particular version of data manipulation. There was a machine learning system named Tay that Microsoft built, and it was supposed to be a Twitter chatbot, so it got put out on Twitter, and of course, the trolls immediately came out and started screwing around with Tay and doing bad things to manipulate what it thought. And Tay turned into a xenophobic, racist, you know, bad thing so quickly that Microsoft had to turn it off, because what it was being trained on was bad stuff. So I want to make that clear. You know, when you think about machine learning systems, the technology of the system that's learning itself is part of the issue, and that certainly carries some risk. But most of the risk has to do with data. Where did the data come from? Are there bad things in the data? Are we modeling the right thing or the wrong thing? And what do we do about that? So here's our simple attack taxonomy, but you know, the problem is that risks are much more general than attacks, and I wanted to address that specifically. We have to do better work in securing our machine learning systems and get past kind of attack of the day thing. This reminds me of what happened in software security, where, you know, in the beginning of the field, it was like, oh, we broke this system, we better fix it. We broke this system, we better fix it in this particular way. And there was a lot of penetrate and patch going on. Of course, we still patch stuff, but it's way better to design things properly in the first place and test their robustness using risk to drive that. So Biml's work, and indeed a lot of security these days, is just as much about creating resilient and reliable machine learning as it is about security. Because security is an emergent property of a system just the way reliability is. And no system that is unreliable or fragile can really be secured very easily. So let's turn to the risk analysis that we did on our generic machine learning model. We've identified 78 risks in machine learning systems in general. Some of those risks apply to the system, but many of them are tied to specific components. 78 may seem like a lot of risks, and it's certainly more than the handful of attacks that people have been talking about. And so it's important to put those into context and talk about where they go. We've also mapped known attacks to attack surfaces in our model, and that's the work that we've been focusing on at Biml. So without further ado, I'm going to dive into the Biml 78 and show you a couple of risks associated with each one of the components in our model. First is component 1, raw data out there in the world, where we identified 13 risks. As I said a minute ago, data play a really critical role in machine learning systems, and in fact are the most important aspect of machine learning security. I think about 60% of risk kind of is carried by data and not about by the other technical aspects of machine learning system. There's lots of raw data out there in the world that is just ripe to be manipulated. And in fact, if you just go any old where and grab your data, there's going to be all sorts of horrible stuff in it. This is something that we can notice when we look at models like GPT-3 that are trained on lots and lots of words from the internet, including places where you probably don't want to spend too much time on the internet. And so GPT-3 ends up learning some bad behaviors along with lots of good behaviors. And it's very hard to separate the good data from the bad data, but it's a super important thing. So let me give you 2 of the 13 risks. Number 1 is what we call data confidentiality. This is important. If you train up a machine learning system on confidential and sensitive data, those data are going to be baked right into the model through training. And so attacks have been developed to extract sensitive and confidential information directly from machine learning systems, and they're well known. So if you're trying to train up a model on top secret data, don't be surprised if the model knows a lot about the top secret data and has its own representation inside. That calls into question, how much does a machine learning system memorize? What parts of confidential or sensitive information are built in there? And if we get rid of those data, what's still in the model? These are important things to think about. So that's one example of a risk. Another is trustworthiness, data trustworthiness. Data sources are not always trustworthy or suitable or even reliable. So how might an attacker tamper with or otherwise poison raw data input? And what happens if input drifts or changes or disappears? If one day there was a big pile of data over there and then we went to go find it again and it's gone, that is a kind of a security risk that you've got to deal with. So those are 2 risks associated with raw data in the world out of 13. There are 11 more risks that you can find in our work in the paper that we put out. Let's move on to component 2. Component 2 is data set assembly, where we've identified 8 risks. Raw data, like I was talking about before out there in the world, have to be transformed into a format that the machine learning system can take. And that means that there's a lot of pre-processing that goes on, there's a lot of picking and choosing and throwing stuff out, and even kind of human level categorizing. And those are all aspects of this data set assembly stuff. Plus there's another wrinkle. Some systems learn all at once and then they're offline, they're learned system, and you interact with that system but it's not learning anymore. And other systems keep on learning while they're out there fielded. That's what's called an online system. Of course it's easier to secure an offline system that doesn't keep learning, though both kinds of systems exist. So I'm going to address that here right now. So of the data set assembly risks, we've identified 2 to talk about. The first is encoding integrity. And so the integrity of your encoding can be introduced and exacerbated while you're pre-processing. So does the pre-processing step itself introduce security problems? Well, maybe it does, because raw bias in raw data can impact lots of things like moral and ethical implications. People think about the fact that we're training stuff on, say, data from historical times where racism was much more rampant, and how do we keep our machine learning systems from learning that racist behavior? And it turns out that's a very important thing to do, but it's also harder than we thought to be able to get these things to be unbiased. So how you transform your raw data into something that ML eats is really, really important. Another example of a risk here is annotation risk. The way that data are sort of tagged and bagged or annotated into features can be directly attacked and introduce attacker bias into a system. So an ML system that's trained up on examples that are way too specific won't be able to generalize well, and a lot of human engineering time goes into ML, it's spent like cleaning data and deleting data and aggregating data and organizing data and just flat out manipulating data so that it can get consumed properly by an ML algorithm. And that's sort of a magical part of ML that nobody's really sure how it works, but all ML practitioners are well aware of that one. So those are 2 risks out of 8 in component 2. Moving on to the third component, data sets themselves. You know, data are grouped into training and validation and test sets. And the way that you divide your data, which you pre-processed, into these sets really has a very deep impact on the model that you train up. Such partitioning is very tricky, and it deeply impacts the future of your machine learning behavior. Let me give you 2 examples of attacks that we found here. The first is a big one, data poisoning. So all of the first 3 components in our generic model, that is raw data in the world and data set assembly and the data sets themselves, are subject to poisoning attacks whereby an attacker intentionally manipulates data in any or all of these 3 components, possibly in a coordinated fashion, in order to cause the ML training to go awry. I talked about Tay a minute ago, Microsoft Tay. That's a perfect example of data poisoning. And data poisoning is a big problem because it's very hard to figure out if your data are poisoned or not, or how much you have to poison your data. That's one example. Another example of data set issues is a transfer attack. Many machine learning systems are constructed because of economic constraints by tuning an already trained base model so that its somewhat generic capabilities can be fine-tuned with a round of specialized training. So a transfer attack presents an important risk in this situation where you have a pre-trained risk that has, pre-trained model that has its own risks, and those get carried over into the new thing. And also, you know, Trojan functionality might be inserted. These are things to think about. There's a new risk in data sets which is not included in our paper that's worth noting here, and that's something that Ross Anderson and some of his colleagues have discussed. It turns out that the order that you present training data in also matters. And if you want your stochastic machine learning system to behave properly, you have to be super careful about randomness and the order that data are presented during training. And in fact, you can manipulate a machine learning model just by changing the order of its training data, not really by changing the training data themselves in a poisoning attack. That's pretty darn interesting and shows you kind of what we're learning as the field progresses in machine learning security. Component 4 is getting to the heart of the technology behind machine learning, the learning algorithms themselves, something like backpropagation, for example. The way backprop works is you put some input in the bottom, it filters up through, you get your output, you compare your output that you got from your system to what it ought to be, and then you make minute changes in all of the nodes and weights going all the way down back to the input. You backpropagate so that basically every time you put in I/O pair into the system, it's adjusting the weights a little bit until it has the behavior, the I/O behavior that you're looking for. There's batching and all sorts of other issues, but that's the basic gist of backpropagation. So we identified 11 risks in this learning algorithms phase, which is the technical heart of ML, but it has less security risk than data. And before I mentioned that there are 2 kinds of basic models, online and offline. And so, of course, offline is easier to secure, as I said before. And in fact, one risk that's an example is an online system that has been trained up and is behaving well, but it adjusts its learning while it's out there in operations. And so if you're a clever attacker, you can cause this thing to drift from its intended operational use case somewhere else. So clever attackers nudge an online system to start doing the wrong thing on purpose. Tay was an online system. It was still learning and it learned to be a troll on Twitter. Another example of a risk is reproducibility. You know, machine learning work has a tendency to be kind of sloppily reported because it's very complicated. And so it's often hard to read a paper and look at even the parameters in the system that are reported in the paper and try to reproduce that work. And if you can't do that, if you can't reproduce it, then it might lead to overconfidence in the model. People might think, oh, this thing works, and other people are not sure that it works. And there's all sorts of issues with kind of the opacity of these things once they're trained up. So that is the reproducibility aspect is an important aspect of ML too. And it has to do with some basic engineering. What exact technology did you use? What were your parameters? Where's the data set? Did you store the data? Are there version controls on that stuff too? These are all things that you have to really think about while you're building these systems and using particular learning algorithms. So there are 9 more risks like that associated with component number 4. Let's move on to component 5. When is training done? And how good is the trained model? That's what evaluation is about. We identified 7 risks in evaluation. Risk number 1 is a well-known risk from a long time ago in machine learning. When I was doing my work initially in 1989, overfitting was a big deal. So a sufficiently powerful machine is obviously capable of learning its training data so well that it essentially just builds a lookup table. It just memorizes everything. So if you memorize all your training data, you're going to be able to perform perfectly on those data, but the question is whether you can generalize outside of the particular training set, and if you can't, that's called overfitting. So if you have a whole bunch of data, even huge piles of data coming into one of these multi-million node things, overfitting is a real possibility because in machine learning today, we've thrown an awful lot of computational power at these problems. So you have to think about that as a risk. Oh, it seems to be performing great, but is it actually generalizing or is it just memorizing? That's one risk. Number 2 is bad evaluation data. If you have evaluation data set that doesn't really reflect the data that's going to happen out there in the real world, and you train up your system, the training set converges, you do your eval set, and it doesn't really reflect what's going on in production later, that can mislead a researcher into thinking everything's working even then when it's not. So evaluation sets are super important. If your evaluation set is too small of a subset, doesn't really reflect what happens out there in the real world in operations, then it's going to mislead somebody. If it's too small or too similar to the training data, it's not going to be very useful, and that's a security risk. So there are 5 more of these risks that we've identified in the paper at evaluation mode. Component number 6 out of 9 is inputs into the operational model itself. Now this is very similar to the inputs we talked about before in the first 3 components, raw data in the world and data set assembly, and then the data sets themselves, because the input that you put into the finally trained up model has to look just like the pre-processed stuff that was in the training sets and the evaluation sets and the test sets. So one of the most important categories of what you're figuring out is what input is fed into the trained model during production, like how's it going to look, got to make sure my training data looks like that. So this is very similar in nature to data set assembly risks and raw data risks that we already discussed. This is where one of the most often talked about and sort of highly touted attacks is, where adversarial examples show up. And so, this is a very important category of computer security risk, and that is, simply put, malicious input. So obviously, input from an attacker might have malicious intent, and the machine learning version of malicious input has come to be known as adversarial examples. Usually what happens is you'll take an input, maybe a vector, and you'll maybe put a mask over it. In terms of a picture, you can change a few pixels, and sometimes if you do this in a clever way, as an attacker, you can cause the whole system to just completely misbehave in a way that's surprising, because a human looking at the manipulated picture, for example, might say, oh, that looks just like it looked before, but the neural network looks at it and says, oh, it's something completely different. So more about that in a minute, because adversarial examples have, though they're important, they've taken up all of the oxygen in the room when it comes to machine learning security. Number 2 is controlled input stream. A trained machine learning system that takes as its input data from outside might be purposefully manipulated by an attacker. So for example, we might, I don't know, put tape over a stop sign or spray paint stuff, white paint on the ground for a self-driving cars. So intentionally controlling the input stream, maybe blinding things with a laser, is another set of attacks that is a way of causing malicious input. And that is one of the 2 out of 5 risks that we have discussed here. So there are 3 other risks that are in the paper. Finally, we come to the model itself. The idea is that we've fielded the thing, we've trained it up, it's out there being operationalized. And this is very similar to evaluation risks in many respects, because when we've got the model and we're trying to determine whether it's trained, we use that evaluation set to figure that out, and now we've actually put it out there in the world. So the first example that we want to talk about is improper reuse. Machine learning systems, as I mentioned before, for economic reasons are often reused intentionally in kind of a transfer situation. So we have one thing that we've trained up, like GPT-3, and then we want to train it on a particular subtask. So we have more specific training. And the risk of transfer of outside of intended use certainly applies. Humans are great at this. Everybody's tried to use a shoe as a hammer. And this happens in machine learning all the time, where we have a system that was trained up to do one thing, and we decide we're just going to use it over here for that other thing, but the people that built it really didn't anticipate that. So improper reuse is a risk number 1. Another example is Trojan functionality. Most model transfer leads to the possibility that what's being reused may be Trojan or otherwise damaged, a version of the model that was being sought out. This is particularly an issue in machine learning because a lot of the systems that people use are open source. They're out there in the world, and they're free to use, but they're not really protected from an integrity perspective. So you just go download the code. You don't even have to check a hash. You just run the thing. And so if somebody puts in a Trojan piece of functionality, that can lead to big problems. And as we've seen in the supply chain attacks of late, this is a real issue, and it's a very subtle way to attack these systems. It's hard to find Trojan functionality and anticipate where people might put it. So those are 2 out of 5 risks. There are 3 more in the paper associated with component number 7. Moving on to 8, outputs. Hey, we're trying to get the machine learning system to do some output, obviously. And so we've got more risks associated with the fielded model. This is where output risks arise. Let me give you 2 examples of the 5 risks we've identified here. Number 1 is an online model again. We've fielded the model. It's out there. It's still learning. And in an online situation, if it's still learning, we might push it past its intended boundaries. So obviously, we have to think about that in a fielded system. Number 2 is inscrutability. Something that I've sort of already talked about a little bit. In far too many cases, a machine learning system is fielded without any real understanding of how it works or why it does what it does. And so integrating a machine learning system that sort of just works into a larger system that then relies on the original ML system to perform properly is a very real risk. A lot of times, because people are not sure how this stuff works, they just say, oh, well, it's magic. And you say, well, the machine learning algorithm said not to give that person a loan, so I guess we won't. And if you can't explain why a system is doing what it's doing, that's really problematic. And that's a thing that really applies to machine learning. So that's 2 of 5 risks associated with component number 8. Finally, we get to outputs themselves. So this is where system output is often the whole point, and direct attacks on the output are pretty obvious. So for example, we can just change the output through a stream directly. This is where an attacker and operational security kind of come together. And it impacts the larger system in where an ML system is encompassed. And so, another non-direct attack is provenance. ML systems have to be trustworthy in order to be put into place. And even a temporary or partial attack can cause trustworthiness to just plummet. This is something that we've seen a fair amount out there in the world. So those are 2 examples of 7 risks that we've identified at the output layer. Finally, outside of the components themselves, we identified some risks, 10 to be particular, which are associated with the system as a whole. Number 1 is black box discrimination. And bias and discrimination are a huge problem in machine learning that has yet to be properly addressed. We've done a lot to identify the problem, but we really haven't figured out what to do about it so far. So many of the data-related component risks that we've talked about lead to bias in the behavior of the ML system itself. So ML systems that operate on personal data or feed into high-impact decision processes like credit scores or employment or recidivism scores or medical diagnosis decisions pose a great deal of risk. When biases are aligned with gender and race and age attributes, operating the system might actually result in discrimination with respect to one of these protected classes, and it's something that's very difficult to anticipate given just the data set in a machine learning model. Bias is subtle, and it's tricky, and it's insidious, and it makes some people think we shouldn't do machine learning at all, especially if we're using historical data from times in society where things were not even as good as they are now, and things are not perfect now. And so that's a real issue in machine learning that we're still working on actively. Number 2 is overconfidence. If an ML system with particular behavior gets integrated into a larger system and it's treated with high confidence, say, oh, users of the system get overconfident. They say, well, it's always worked in the past, and then it sort of falls off the edge and does something maybe a little bit surprising, but it's always worked in the past. You might say, well, it's fine, it's always right. We're not going to give that person a loan or whatever because the ML system said that. Developing overconfidence in machine learning is made way easier by the fact that most people can't describe what their ML systems actually do. They're a little bit vaguely described. So that's 2 out of 10 risks at the system-wide level. Now that's a lot of risks that we've just covered. I've covered 20 risks, 2 for each of the components, and 2 system-wide risks so far in about 30 minutes. And there are, 48 more, something like that. No, wait, 68 more. No, 58 more. That's it. My math is good. So 78 risks is an awful lot. What are you supposed to do about these risks? And that's something that we're all actively working on right now. There are groups working at Google and Microsoft and Facebook and OpenAI. There are independent groups like ours at Biml. There are academics working on this sort of risk analysis stuff. And there's even some government groups at NIST that are trying to figure out what to do about machine learning security risks. And right now we're at very early stage in the field where we're still identifying stuff. In fact, my theory is that we could pretty easily expand our list of 78 risks into 100. So, what are we supposed to do about all these? Oh, that's a good question. Now, in order to make this a little bit simpler, what I want to do is talk about the top 5 machine learning risks. So I've told you 20. Now we're going to rank them, rank all 78. So we're throwing it out, even more, and we're going to go to the top 5. These are things, a couple of which I've already discussed, but it's worth diving into them a little more deeply. Number 1 is adversarial examples or malicious input for machine learning. So this is probably the most commonly discussed attack. It's how you fool an ML system by providing malicious input often involving really small perturbations that cause the system to make a very bad prediction or categorization. So here on this slide you can see a school bus and a pheasant and a Mayan temple in one column. And then in the middle you can see these masks that overlay those three pictures. And on the right you can see what looks like a school bus and a pheasant and a Mayan temple. Gosh, it looks like the mask didn't do anything in terms of human perception. But if you show these to a particular ML model, they're all three categorized as leopards, which is not what they are. And so that gives you an example of what happens when you just do some very small tweaks to one of these visual systems using adversarial examples. So though there's a lot of coverage and resulting attention paid to this problem, it is important. There's lots of other stuff out there that's not adversarial examples. Of course, if you think about particular problem sets like facial recognition or self-driving cars, you can see why this is the number one risk. Number two is data poisoning. We already said you got to be super careful of data out there. You know, data play an outsized role in the security of an ML system. So if an attacker can intentionally manipulate data being used by an ML system at any level in a coordinated way, then the entire system can be compromised. So data poisoning attacks require really special attention. You know, one question you have to ask yourself is, which fraction of the training data can an attacker control, and to what extent can they do that? We already had a good example of data poisoning from Microsoft Tay. Number three is online system manipulation. Remember, an online system is one that keeps on learning. So when you continue to learn during operational use, you're modifying your behavior in real time, and a clever attacker can nudge the still learning system in the wrong direction on purpose. This slowly retrains the ML system to do the wrong thing, or the thing the attacker wants it to do. This is a really complicated risk because it demands that ML engineers consider a bunch of things: data provenance, algorithm choice, and systems operation in order to properly address it. You can't just address it at any of the life cycle phases. Instead, you got to address it at all the life cycle phases, and that makes it a much more challenging kind of risk than some of the others that have a particular phase that they're tied to. Online system manipulation is a real thing. Number four, transfer learning. We've also discussed this one. This is something that's been talked about in the literature a fair amount since about 2017. So in many cases in the real world, we're retraining an ML system. We're taking advantage of the fact that we've got an already trained thing, and we want to fine tune it to carry out something specific. And a data transfer attack might take place when the base system is compromised or otherwise unsuitable, making unanticipated behavior, maybe defined by the attacker in the Trojan sense, possible. And that's a risk you got to think about. So that's number four. Number five, we addressed at the very top of this talk, and it's worth picking up this stitch again. Data protection is a difficult problem. It's difficult without even throwing machine learning into the mix. But one of the unique challenges in ML is that we have sensitive or confidential information. We shove it right into the system through training, and it's all built right into the model. So even if we delete those data, it's still in there. And so, memorization in a model is a real thing, and often we can extract it. So subtle but very effective extraction attacks against machine learning systems data are an important category of risk, and that's number five. So that's the top five risks. And so what I've given you today is an overview of machine learning security risks associated with particular life cycles in a generic machine learning model. And we've talked about 78 of those. We have reviewed the top five, and now what we need to do is figure out what to do about all those risks. We haven't gotten to that yet. but that's something that we really need to work on. Machine learning security is not as simple as only addressing malicious input. It's not as simple as only only thinking about data provenance. It's not as simple as saying, oh, well, we know that those data are racist, so we're just going to have to put up with this. Instead, we have to think very carefully about engineering trade-offs that we make while we're building systems. And so that's what we're working on now at Biml. I want to give you some pointers to where to learn more on this last slide. Here are 3 URLs. The second one is the most important. That's to the Berryville Institute of Machine Learning, which has the URL berryvilleiml.com. We welcome your feedback and your questions and your comments, and thanks for listening to this episode of Biml in the Barn. Now we're going to have a couple of questions from the Biml audience. So how about if we turn it over to you?
Who does ML in an organization?
That seems like a pretty simple question, doesn't it? But it turns out that it's not. If you're in a large organization, figuring out where all the ML is a challenging issue. And in fact, there are lots of different groups who do ML. One group might be the data science people. Another group might be computer scientists. Another group might be software engineering. Another group might be the product people who use a prefabricated machine. Another group might be technical support, who instead of having a human answer the phone, has GPT-3 answer the phone and have a little conversation with you to shove you into the right bucket. And so machine learning is kind of popping up everywhere like mushrooms after a spring rain. And one of the issues is how do you find it all? But more importantly than that, and I think maybe at the heart of your question is this. Data science people and computer scientists and software engineers all have different approaches to this engineering exercise, to ML. And they're so radically different that sometimes if you went to a software engineering person and said, hey, do you have, revision control in your software pile? They go, of course. What do you think? I went to kindergarten. Of course I do that. If you go to somebody in data science and say, hey, do you have revision control? They go, what's that? So it's sort of a different kind of way of approaching the problem. And that leads to a big challenge in organizations that are doing lots of ML or maybe don't even know they're doing lots of ML, which is, how do we take something like the Biml 78 and apply those to these different groups of people? And I think, we have to come up with ways of thinking about or understanding how each of these kinds of groups out there does their work. And one of the first challenges, I guess, in any large organization is just finding out where the ML stuff is. It reminds me a lot of, back in the early days where you used to say things like, well, where's the software? Now imagine going to any organization on earth today and saying, in your company, where's the software? And there are no companies that have no software anymore. There's software risk everywhere. And I predict that machine learning risk is going to be very much the same, soon enough. It's growing so fast, and it's such a widespread phenomenon. It's going to be everywhere soon, and lots of different kinds of people are going to be working with it.
Yeah, the complexity that you're describing was something that had come up earlier in my head, and it combines with the number of risks. So, the Biml 78 risk list is a really long list.
Yeah.
So, how do you track these? How do you mitigate this when you already have all this diversity among the people that might be responsible?
Yeah, let's sort of narrow it down to a particular ML project. Let's say I've got an ML project. I know what we're doing. What do I do with this Biml 78 pile? And I think the first answer is to identify which risks apply to you, to your situation. So you take the 78 and you go, all right, I can see those life cycle phases. I have those. Let me see which risks apply to me. Identification is actually half the battle, because sometimes if you identify a risk, you can properly manage it just sort of by caveat. The identification does most of the work. But in other cases, it's not. And in some cases, like say online learning, you might have to set up some sort of monitoring situation. So you want to set up, kind of a, what do you call that? A trajectory for your system. So we're going to keep track of our system while it's running. We're going to look at telemetry data all the time in order to find out whether it's actually doing what we thought it was going to do because we have an online model. And so, it really depends on the nature of those risks. But I think setting up mitigations is something that's within the grasp of possibility right now. And in some cases, there are things that are a big challenge. Like if we want to use public data and those public data are available for everybody to manipulate, what are we going to do about that? Or if, say, we're trying to recognize language from a possible adversary out there, what do we do about that? When they might intentionally be feeding us bad stuff that we feed into our models. And so these are all things we got to figure out. I think we're at the very beginning of this field, and we need to come up with a number of techniques to toolify, to automate, and we haven't done that yet. I haven't seen yet a sort of startup in machine learning security that's doing anything that begins to even address these 78 risks. Lots of work to do.
Yeah, there was a story this week which I think is one of the more prominent sort of ML in the news stories currently, which is that Facebook is saying that it's going to discard a lot of their face data, more than a billion
people
images of faces. But they've also said that they're going to keep the models and that they may use them in future products.
Right.
So a lot of conversation around how this impacts privacy, whether this is an advance for privacy. What is it? How much progress are we making?
None. This is a representational sleight of hand, which is incredibly clever and borders on evil, not surprising coming out of Facebook. Because they're trying to get PR kudos for deleting billions of raw face images. But at the same time, they're keeping the model and they're keeping the face-to-vec data around. And that's just a different representation of the same data, right? We all know that machine learning models have a tendency to memorize their stuff, especially really, really big ones. And we all know about data extraction attacks. We've known about these for years and years. So all of those things apply. And it is incredibly disingenuous to say, if we just delete the raw data, everything's fine here, pay no attention to the ML security risk or privacy risk. So, in a word, it's BS.
Treating me like something that you left behind to stay. Now I'm not sure that I can give a damn.